Let us now take a look at the structural or photometric properties of spiral galaxies. First, about spiral galaxies in general. They do have a lot of diversity in their structure and components. First of all, there is the degree in which their spiral arms are prominent, which was, of course, the basis of Hubble classification, as well as the ratio bulge to disk. And because bulge and disk have different stellar populations, bulge being an old one, disk being younger, there are all these differences in star formation rates and colors and so on. The disks, of course, have interstellar material, cold gas and dust, from which stars are forming. Also, spirals tend to avoid dense regions of the large-scale structure because this is where galaxy mergers can happen, or did happen, and those spirals have been turned into ellipticals. Recall the trends that we discussed about Hubble sequence. Spirals, of course, participate in all of them. Most of the trends is along the spiral branch, and they're listed here. But basically, as we go from early Hubble types towards the late ones, there is an increasing amount of star formation, increasing amount of gas, and increase in the disk to bulge ratio. All of this manifests itself in colors. They get bluer, and other measured photometric properties. So let's look at individual subcomponents of spiral galaxies. First, there are the disks, and they're characterized by exponential distribution. We'll show that in a moment. And there may be more than one kind of disks. There are thin disks within which star formation occurs. That's where the interstellar material is. But they may be embedded into thicker disks, composed mainly of intermediate to old-age stars. The bulges are essentially little ellipticals in the middle of spirals. Not all spirals have bulges. Some simply have disks that go all the way to the middle, maybe rounded off, but no distinct elliptical-like component. Now, unlike Bade's original idea of population 2 stars, they're supposed to be metal poor. Stars in halo are metal poor. Those in galactic bulge, as well as in ellipticals, are actually metal rich. They did result from substantial amount of chemical evolution, but very early on. And again, there is the important difference in dynamics. The disks are rotationally supported against self-gravity, and bulges are pressure supported, random motions. About half of all spirals contain bar-like feature, and you've seen pictures. Sometimes spiral arms begin at the ends of the bar. Bars are similar to bulges in their composition, but dynamically they're distinct. In their very centers, some people argue that spirals contain an additional component concentric with the bulge itself, which may be very dense. Sometimes it may contain supermassive black hole, which may or may not be active, and there is usually some star formation. If you remember numerical experiments and collisions of spiral galaxies, the gas tends to sink to the center because it loses energy, and if you accumulate a lot of gas at high density, it will tend to make stars. In contrast to that, the most extended stellar component is the stellar halo, and that is composed out of metal poor stars, kind of stars that make dwarf spheroidal galaxies. So we believe that all of the stellar content of the galactic stellar halo is from disrupted, merged dwarf galaxies that have been torn apart by tidal forces, and they're populated the halo, and there is a lot of good experimental evidence for that. And of course, there is the dark halo. Dark halos are more extended than the visible parts. There are some hints as to what their radial distribution could be, as well as their shape. They're probably triaxial ellipsoids. So the way we can quantify distribution of visible material is through surface photometry, meaning. But before we look at the distribution of stars, we first need to correct for the inclination effects, because face-on spirals are more or less circular, so their apparent ellipticity in the sky tells you what the inclination is. Then we have to correct for the interstellar extinction, both in the galaxies themselves, but also in the Milky Way, in the direction that we look towards them. Usually, these radial surface brightness profiles are obtained by averaging in circular or elliptical annuli, and so that tends to average over the spiral arms. As it turns out, typical surface brightness profiles of spiral disks are exponential. The projected surface brightness declines exponentially from the center out, and the e-folding lengths or disk scale lengths are of the order of few kiloparsecs. So if you measure a surface brightness profile of a galaxy, then you'll see something like this. If plotted on semi-log plot, log surface brightness versus linear radius, an exponential looks like a straight line. And indeed, that's what you see in the outer regions. There is extra light in the middle, and that's due to the bulge. And so one can then fit an exponential disk plus the bulge component using one of the elliptical galaxy fitting formulae that we will look at in the next chapter, and does decompose the light into bulge and the disk. So this is now a well-established procedure, and many galaxies have been studied in this way. Here are examples of a few. Now here are some contour maps of the surface brightness distribution of spiral galaxies in the sky. I mean, these are lines of equal brightness, and to anticipate something I'll show in a moment, they do seem to stop at some point. So what about perpendicular structure? I mean, along the radius from center out, they're exponential, but turns out the distribution of density in spiral galaxies perpendicular to the plane of the disk is also exponential. And the typical scale height is of the order of hundreds of parsecs, much shorter than the disk scale length of several kiloparsecs. So one interesting thing about spiral galaxies is that their disks have cutoffs. They do have an edge. Past certain radius, there are no more stars. However, hydrogen, from which stars are made, usually extends further, and the dark halo further yet. So that suggests that disks may be forming from the inside out in terms of star formation. So if you measure the profile, you can take the integral under it, and that gives you the total luminosity of the galaxy, or its two components, the bulge and the disk. Inclination correction tends to be the trickiest of them all, but we know how to do that. And the extinction correction depends on estimating the amount of dust along the line of sight. Because the interstellar extinction causes reddening, absorbing more blue light than red light, using colors can give us indication how much reddening there is, and from that, how much of total absorption there is. Next time, we will talk about interstellar medium, gas in spiral galaxies.